Good afternoon, class. This is Tuesday, June the 9th of 2020, Coronachem day 44. Your homework yesterday was to do two questions, 1573 and 1574 as part of our review for chapter 15, which is on equilibria. So I'll read the question for you, where they ask us to do an assessment of where the equilibrium, where the reaction is headed as it approaches equilibrium. So 1573 asks, the reaction of PCl3 plus chlorine gas to give PCl5 gas, phosphorus pentachloride, has a Kp of 0.0870 at 300 degrees Celsius. A flask is charged with 0.5 atmospheres of PCl3, 0.5 atmospheres of chlorine, and 0.2 atmospheres of PCl5 at this temperature. A. Use the reaction quotient to determine the direction the reaction must proceed in order to reach equilibrium. So here's the reaction. So equilibria are established by putting concentrations or partial pressures in the form of products over reactants. It's always products over reactants. So the reaction quotient is determined using the same type of calculation as you would to determine the equilibrium constant. So the partial pressure of the products divided the partial pressure of the reactants. In this case, PCl5 gas pressure over the pressure of PCl3 gas and Cl2 gas. What you get is 0.2 over 0.5 times 0.5. The reaction quotient, therefore, is 0.8 when you do this math. And Kp is 0.087. So the Q is a lot larger than Kp. And that means that to make this number smaller, you have to either reduce the numerator or increase the denominator, or both. How is that going to happen? Well, you reduce the numerator by producing less of this and more of that. So that means the reaction is going to move left. And since the reaction is going to move left, we could set it up so that when we answer the second part of the question, the ice table will have a value minus x. As it turns out, when I did the ice table, I put the x in the wrong direction, but it doesn't matter because the math works out anyway. So I'm going to show you with the results I obtained with the wrong assumption for the direction of the movement. But because the math works out anyway, I'll show you how that. I'll show it to you this way so you can see that as long as you follow the math, you'll still get the correct answer. So let's set it up. I'm going to leave the equation on so you can see where I'm getting everything. So we set up an ice table, and I initially wrongly assumed that the reaction was going to move to the right. But I just said, okay, let's let x be the decrease in PCl3 concentration. So at equilibrium, it's going to be 0.5 minus x according to my assumption. But the nice thing about the math is, you can get a negative number, and if you're working with equilibria, it is possible for the equilibrium to move the opposite way than what you thought it would move, and you'll still get the correct answer as long as you recognize what's going on. Okay, so I said let x equal the increase in PCl5 partial pressure. The assumption is that the reaction will move right. If x is a negative number, that means it moved left. So we set it up, and we got the following equilibrium. Kp is equal to 0.0870 at that temperature, and the concentration at equilibrium of the PCl5 is going to be 0.2 plus x according to our assumption, and the concentration of these two things is going to be 0.5 minus x, and I'll simply square that because they're both identical. When you expand the thing, you get a trinomial, so I'll just jump to the trinomial, otherwise we're going to be using up a lot of space. So it'll be 0.87 squared minus 1.087x minus 0.17825. That's the trinomial you get when you expand that expression. And here's a perfect opportunity for me to show or to check my results using the quadratic formula, because in my notes I actually originally did it using the quadratic formula. I might as well show you. Hopefully the camera will focus. So that's what I did originally, and the results I got were like that. I'll show you how we can do it with the calculator. So I'm going to enter the trinomial into the calculator. So I'll go into mode, equation, quadratic. The first value is 0.087, so 0.087, enter. Second value is negative 1.087, and the third value is negative 0.17825. 0.17825. Okay, and the answer I get is 1.26. It's either 12.656 or negative 0.161. So at first sight, the positive number seems like the correct answer, but it isn't, because first of all, you only have 0.5 and 0.2. So if you get 12, where's it coming from? You can't get that as an answer. So you can discard the first answer, 12.656 1388. That's not possible. And the second answer it gives you is negative 0.16 188 5912. So that confirms that my assumption was incorrect. The reaction actually moves to the left. I assumed the reaction moves to the right, and so that this was going to decrease. As it turns out, it's moving to the left, so it's going to go higher than 0.5, so it'll be a double negative. So let's now show how that looks when you work it out. I always feel an internal resistance to erasing the board right after I write something, but it's on video, so you can always rewind. You do it in the classroom, you get an instant write. So to find the PCl3 concentration starts off at 0.05, and I assume there was negative x, but x is a negative number, so when I plug in the number, you get this. Or 0.2118859.138, which you will round off to 0.21 atmosphere. So that's the pressure of the PCl3. PCl2 is going to be the same, of 0.21. It's the same calculation. I'm not going to write it again. And then PCl5, partial pressure of PCl5 is going to be 0.2 plus x, but x is negative, so it's going to be 0.2 minus 0.16188, etc., which is going to give you 3.81 times 10 to the minus 2 atmospheres at equilibrium with the correct number of significant figures. So in part C of the question, it asks, what effect will increasing the volume of the system have on the mole fraction of chlorine in the equilibrium mixture? So increase the increasing the volume of the system have on the mole fraction of Cl2. Increase the volume of the system, it will move left, because you have 2 moles going into 1 mole. So if you give it more volume, if you decrease, if you give it more space, the system tries to react by reestablishing the equilibrium that's been disturbed by creating more volume. And the way it's going to create more volume is by having more of these appear. So it will move left. More space for molecules allows the left with 2 moles of gases versus right with only 1. So it will expand in the direction to increase the volume of the gases that are in the reaction. Then in part D, it asks, the reaction is exothermic, meaning it gives off heat. What effect will increasing the temperature of the system have on the mole fraction of chlorine in the equilibrium mixture? If the reaction is exothermic, then heat can be looked upon as a product, so the heat would appear here. Adding this product will push the reaction to the left, because if you increase the concentration of the heat, then the reaction will move in the direction of reducing the heat. So it'll move left. The chlorine gas pressure will increase, because if you move left, obviously you produce more chlorine. And that's it for that question. 1574 is the next one, and it's another fairly, it's not complicated, it's just long and tedious because you have to interpret the results after you get them. So it covers a couple pages, so I'm going to do that now. Begin by erasing. Ooh. So 1574. It's H2 gas plus I2 gas gives you 2HI at 458 degrees Celsius in a 5-liter container. All of this is, well, this is important at any rate because you have to calculate the concentration. So you initially have 0.112 moles of the hydrogen in the 5-liter container. So that's going to be 2.24 times 10 to the minus 2 molar concentration, moles per liter. Same thing for the iodine gas, iodine vapor. I guess I should say iodine, because we say fluorine, bromine, chlorine. Why do we say iodine? Or why do I say it? I don't know if other people say it. And then 2HI is 0.775 mole, and there's 5-liter container again, so that comes to 0.155 molar. Now we can, well, let's find out what it's asking us before we do anything. An equilibrium mixture of H2I2 and IJ at 458 contains 0.112, 0.112, and 0.775. Yeah. In a 5-liter vessel, what are the equilibrium partial pressures when equilibrium is established following the addition of 0.1 mole of HI? Well, let's first of all find out what Kc is. It's going to be equal to the hydrogen iodide concentration squared over concentration of hydrogen times iodine. So that we're going to find out equilibrium. We're assuming this is at equilibrium before we start adding anything to it. Yeah, because we're going to add something to it after. So here we go. It's going to be 0.155 squared over the 2.24 times 10 to the minus 2 twice, so we're going to square that too because both of them have the same constant. Rather than write it twice, we'll just do that. And what we get is 47.88 1457 27, and then we're going to disturb the equilibrium, so I should write this again to show the disturbance of the equilibrium. We're going to use an ice table to determine what happens. So initially we're sitting at 2.24 times 10 to the minus 2, 2.24 times 10 to the minus 2, and 0.17. Why did I put 0.175? Oh, that's why. Because they added 0.1. So we're going to disturb the equilibrium, and we'll call it initial. And yeah, excuse me. We disturbed the equilibrium by adding 0.1 to the 0.775. So if you take 0.775, add 0.1, and then divide that all by the 5 liters, what you get is 0.175. So we did a little preliminary calculation. That's what we're putting here, 0.175. Now we've disturbed the equilibrium, so likely it's going to move left. So this is going to increase. This is going to decrease by an amount x. So an equilibrium is going to be 0.175 minus x. And because this decreases by x, these will increase by 1/2 x, because the stoichiometry is 1 to 2. So you're going to have minus 1/2 x here and a minus 1/2 x here. And then we're going to have at equilibrium is 2.24 times 10 to the minus 2 minus 1/2 x in both cases. And now let's set up our equilibrium expression. I have to erase everything now. Now this is a small problem to write in the book, but to do it, it ends up taking up a lot of space in your notebook. So this is what you end up with. Kc is equal to 47.88, which we figured out in the last step. 145,727, and it represents concentration of Hi raised to the power of 2 over concentration of H times I, diatonic. And numerically, it's going to look like this. All that squared. When we expand it, we're going to get a trinomial, and it looks like this. 11.97036432 x squared plus 1.072544 643 x minus 0.150975. This is a nightmare to do using the quadratic formula. So I'm going to do it with a calculator just to corroborate my own results. Hopefully I get the same answer. Okay, again we're going to turn on that function, mode, equation, quadratic. The value of A is 11.97036432. Enter. Part B is 1.0725446643. Enter. The nice thing about it, when you enter it in your calculator, if you enter a wrong number, you can always go scroll back through it and re-enter the numbers, and the calculator will just recalculate for you. When you do it on paper, yeah. And the last part is negative 0.150975. Okay, so what I get is 7.61 times 10 to the minus 2 and negative 0.1675. So after the addition of 0.1 moles of HI to the reaction, still the concentration of HI momentarily rises to 0.175 mole. That's before the reaction starts. But now it begins to equilibrate. This causes a disturbance of the equilibrium, which shifts to the left again. The only value of x that makes sense is the positive one, because it leads to a reduction of the concentration of HI. So HI concentration. So I got the same answers with the calculator as I did with the quadratic formula, so that's reassuring. So the HI concentration after the equilibrium is reattained is going to be 0.175 minus x, and the correct, I didn't write the values of x. So there's two values of x that you get. They are 7.611086.834 times 10 to the negative 2 and negative 1.65710868 3 times 10 to the minus 1. So this is the one that makes sense. This doesn't make sense because it would mean that you've added stuff and then the concentration increases. That wouldn't make sense for it to happen that way. So HI concentration is going to be equal to 0.175 minus X, which equals 0.175 minus 7.611, etc., times 10 to the minus 2. What you get after sig figs is, actually no, I'm not going to put the sig figs, it's 9.888913.166 times 10 to the minus 2 molar. Then the I2 concentration is going to equal the H2 concentration, and it's going to be 2.24 times 10 to the minus 2 plus 1/2 X, which comes out to 6.04554 times 10 to the minus 2 molar. What are they really asking over?
What are the equilibrium partial pressures when equilibrium is established following the addition of 0.1 molar?
You're going to use PV equals nRT. So you have that many, that's the molar concentration, and you have 5 liters of the stuff. Means you got 0.302. What is this? Yeah, you gotta have it, they say partial pressure, so you gotta go to pressure. So you get 0.3022771709 moles of gas in a 5-liter container. That's the concentration of the, did I include this for the total concentration, or did I skip a step? Okay, I see what you mean. Okay, yeah, so I calculated each one individually. So I'm going to scroll back to the beginning. Continue my calculation. So I have that many moles of gas in a 5-liter container using P equals nRT, and we're solving for P. So we're going to get nRT over V. Enter the values. You got 0.302, etc. moles of gas. Gas constant 0.082057. A liter atmospheres per Kelvin mole. The temperature is, you have to be in Kelvin. Temperature is 758.15 Kelvin. I really scrunched that up. And then 5 liters of the container. So the pressure you get after sig figs is 18.8 atmospheres. Both of those gases each have a partial pressure of 18.8 atmosphere for H2 and I2. Then if you want to find the partial pressure for the HI, the pressure of HI is equal to 9.888, etc., times 10 to the minus 2, again times 5 liters. So that means you have 0.4944456583 moles of that gas, of HI. Again, you do the P equals nRT, solve for P. I'm not going to do that on the board. What I got was 6.15 atmospheres of HI. Okay, and that's partial. It's a long question. It's got multi-steps in such a short little question. what are we gonna do? I wanna give you a mock test for tonight. And today is Tuesday. Try doing it tonight, because we are getting kind of pressed for time. So this is what I'll give you as your mock test. If you can solve without getting stuck, good for you. I'll be proud of you, and you'll be proud of yourself, because it's a lot of material in a short time. So here's your mock test for tonight. Try it, and tomorrow I will solve it for you. And then eventually I will give you the real test. And a ton of marking for myself. Mock test. So 4 questions as usual. And it's 1521, 1531, 1543, and 1568. Let me double check that one. Well, 68.
Looks like you've already done 68 at some point. Okay, no, it's okay.
So that'll be your mock test. So do those 4 questions tonight, and we'll review them tomorrow. All right? And I'll see you tomorrow.